Energy changes. Energy can appear in a number of different forms. It can transform from one form to another. For example, a skier transforms their gravitational potential energy into kinetic energy as they come down the slope. Energy is always conserved in these changes, but not all the energy becomes the type we want. Often unwanted heat or thermal energy is produced and then lost to the surroundings. We'll look at some of the ways of calculating these different forms of energy, starting with work done. Well, work done is equal to the force exerted multiplied by the distance moved in the direction of the force, and this is equal to the energy transferred by the body doing the work. If we have an object here with a force F exerted on it, and it moves like this, a distance s, the work done, W, is equal to F times s, force times distance or displacement. If the force is at an angle theta to the motion of the box, like this, we could resolve the force and find that the component of the force in the direction in which the object moves would be F cos theta. And so, as the object moves, the work done will be given by Fs cos theta, the F cos theta being the component of the force in the direction of the displacement s. We can use the idea of work done to find out how to calculate gravitational potential energy, the energy an object has due to its height. Here a force F acts vertically upwards on an object, and if the object is to move up at a constant speed through a height delta h, the force needed to move it at a constant speed must be equal to its weight. Now, weight is equal to mass multiplied by gravitational field strength, or mg, and so the work done, and therefore the change in gravitational potential energy, delta EP, change in gravitational potential energy, is equal to the force, or the weight, mg, times the height change, delta h. Now let's look at how to calculate kinetic energy. Well, going back to work done is equal to force multiplied by distance, but we also know that force is equal to mass times acceleration. So replacing the F term with ma, we get that work done is equal to mass times acceleration times distance. Looking at the equation of motion for uniform acceleration, v squared equals u squared plus 2as, where v is final velocity and u is initial velocity, if we consider the special case where the object is accelerated from rest, and therefore the u term is 0, we can write v squared is equal to 2as. Rearranging, as is equal to v squared over 2, but as appears in this term here for the work done. So, the work done on accelerating a body, and therefore the kinetic energy gained by that body, which we can write as E subscript k, is equal to half times mass times speed squared. Moving on to elastic potential energy, the energy stored in a stretched spring. Here we have a spring of length L, and if we stretch it and give it an extension delta L, we could plot a graph of the extension delta L against F, and as the force increased, so would the extension, giving a straight line through the origin. The area under this will be in units of force times distance. That was the units of work. And so the area underneath will give the work done on stretching the spring, which will be the energy stored within the spring. The area of a triangle is half times base times height. In this case, half times the base F, the force applied, times the height of the graph, which is delta L, the extension. So we can write that the energy stored in the spring is equal to half the force multiplied by the extension delta L. Now we'll look at all these relationships together. We found that the work done is equal to force times distance times the cosine of the angle between the force and the direction of motion. We found that the change in gravitational potential energy, delta E subscript P, is equal to mass times gravitational field strength times change in height. Kinetic energy, E subscript K, is equal to half mass times speed squared. The energy stored in a spring is equal to half the force multiplied by the change in length. And now we'll look at how these relationships can be used to solve several problems. Here we have what on the face of it is a very complicated problem. A force of 250 newtons is used to stretch a catapult by 0.5 meters, which is then used to fire a 500-gram stone directly upwards. We need to calculate the energy stored in the catapult, the initial speed of the stone, and the height it reaches. Well, the energy stored in the catapult. We know that the energy stored in a spring is given by half F delta L, which in this case is half times the force 250 newtons times the change in length of half a meter, meaning it has an energy of 62.5 joules. Next we're asked to find the initial speed of the stone, and this is where conservation of energy really helps. We know that the energy stored in the catapult will have become the kinetic energy of the stone, but we know that the energy stored in the catapult was 62.5 joules. Therefore the initial kinetic energy of the stone will be 62.5 joules, meaning we can write 62.5 is equal to half mv squared, the kinetic energy of the stone, which is equal to half times 0.5, the mass, which must be in kilograms, times the speed squared. Rearranging, we get that the speed is equal to 2 multiplied by 2 multiplied by 62.5, which is the square root of 250, or 15.8 meters per second. This seems a reasonable speed. Finally, we're asked to find the height the stone reaches, and conservation of energy helps us again. In this case, the kinetic energy of the stone will become gravitational potential energy as the stone gains height. At the top of its climb, it will have no kinetic energy, and therefore the whole of its energy will become gravitational potential energy. That is still our 62.5 joules. So we can write that 62.5 is equal to the gravitational potential energy mg delta H, which is a mass of 0.5 kilograms, gravitational field strength 9.81 newtons per kilogram, multiplied by the change in height. And it's the change in height we want to find, so we can rearrange the equation to give change in height is equal to 62.5 divided by 0.5 and 9.81, giving a maximum height of 12.7 meters. Always consider your answer. Does this seem reasonable? Yes, it does. If the problem involved forces moving through distances, we could also have the energy turning into work, or work turning into energy. With these situations, you're given the facility to calculate the energy in one circumstance, and then you can assume that that energy is the same in the second and third and maybe further circumstances. In this second example, we have a high jumper at the top of their jump. So we'll mark their position here, and at the moment they have gravitational potential energy given by mass times gravitational field strength times the change in height. They're going to drop down to this position, which I'll mark with this arrow. So the change in height is from their top position to their bottom position. The energy has now been stored as elastic energy in the crash mat, given by half times the average force exerted by the crash mat on the jumper, times the compression of the crash mat, and this distance here, delta L, gives us the compression of the crash mat. If the temperature rise of the mat can be considered as negligible, the gravitational potential energy of the jumper at the start, mg delta H, will equal the elastic energy of the crash mat, half F delta L. So you'll see the bigger L, the bigger the mat is able to compress, the smaller the force will have to be on the jumper.